if nothing else, nothing about complex oxides, you should at least remember the full form of GYAN. And that is Global Initiative for Academic Networks. See, there is a viewpoint these days that everything can be learned through internet. And when you just download, upload, and do this PDF, and all these books are available, that everything is available in the internet. All the courses of MIT and Harvard are also in the internet. The GYAN program of MHRD wants to demolish that idea. For true learning, you need a guru, a true teacher, and students who are interacting actively. So this is like building some kind of academic network. The chance that this gives you, along with the lectures that you'll be taking and along the, what you'll be learning new things, the critical component is interacting with the visiting faculty. And all of you should take this chance of, talking to Professor Yom and, learning and sharpening your ideas and building up academic network. In the future, if you need some help, hopefully Professor Yom would respond to your emails and any academic doubts. So that is the purpose of the GYAN program. Professor Changung Yom, I met first time way back in 2001 or 2000, maybe 2000.
I joined 2000.
2000. So 2000, I was doing my postdoc at Wisconsin-Madison, and you came from Duke?
Yeah, Duke. Yes.
Duke University. He's a prolific researcher. And I don't think, in terms of nature and science, maybe around more than 10 probably, right? There's several papers in Nature and Science, very high impactful research. He's the editor of AP Materials. He did his PhD from Stanford, the famous KGB group, then postdoc at IBM, AT&T Bell Labs. So in terms of the background, he's the best trained superconductivity person at that time. Then he's now a full professor in physics and material science and engineering at Wisconsin-Madison. And prolific teacher, a big group of students have been trained through him. It's a really good opportunity for all of us to learn about complex oxides and superconductivity, multiferroics, all these different aspects of condensed matter physics. He covers them. He's an expert in film growth, but even the physics aspects of the designing aspects, devices. So that is, it's a wonderful opportunity for all of us to learn something new and strengthen our understanding through this GYAN course. So thank you very much for being willing to be part of this GYAN program, and we hope that everyone can learn something new. Thank you
very much. Well, first I'm very happy to be here, and then honored to give this GYAN lecture, and then especially Satyavrata is a good friend, but I respect his science, and then what he does is I respect a lot. And then this is my first time visit India here, and then I think I visited here several places before I came here, and then it's a wonderful people, and then it's a beautiful country, and then I really enjoy being here. And then so the next 10 days. Almost 2 weeks, and I hope we can learn each other, I get to know each other. So this is exactly what I feel very important. I mean, current a lot of important research is especially is more complex, and then collaboration is very important. And also I'm very fortunate to have many talented collaborators and benefit from those. So. And then hopefully, I think we know each other, and then building some collaboration. I hope. I'm happy to provide any resources and then samples. We grow a lot of samples, and then there's an opportunity to do that. So I'm giving this lecture here, but I think I'd like to have a more interactive, and then so we can interrupt in the middle. You can ask questions. Feel free to do that. And then I have a number of slides, but I think my objective of the sharing of these the slides and the work is not just knowledge transfer to you, and then that's exactly what Satyapra said. You can Google and you can watch the videos, and then you can see a lot of information and tremendous information. But I think what I'm trying to relay in these lectures is not really just transfer, I mean, just giving lectures about the knowledge and then some basics. I think more importantly, how we approach the science to understand the actual materials and physics. And then our unique way of the multidisciplinary and collaborative research is very beneficial. So I like to share some of my lot of experience. Maybe that's rather just after a few years from my lecture. Maybe you forget some of the details, but I think of something how you can be more how creative and approach to your science. I think that's my major goal. And then so it's coffee break. We have a lot of time to talk, and then so I mean also I'm gonna share some of my how I came here that far, and then how I learned from many people. Okay, that sounds good. All right, let's start my lecture here. First, this lecture is a many components of this, and then at the end I'll give you why with these lectures has a series of like structure and synthesis and then characterization and device, and then we cannot cover all of them, but I think I have some highlights of important pieces, and then at the end you'll actually understand why actually this all the lectures connected, so you know the connecting dots at the end. So I think that's the main purpose of this. So multifunctional complex oxide, that's the field, and evolved from high TC superconductor, especially in thin film field. And I got my PhD in 1991, but at the time I joined my PhD the advisors group, we call KGB, and then in 1986, that's the time high TC was discovered. And when high TC is discovered, and then at the time, that even we did not know what the actual material shows the superconductivity, high temperature superconductivity. That's a real breakthrough in science, and then both chemistry, physics, and material science, in all the interesting the discoveries, and then science was performed at the time. But after that, I think this field is evolved. Is all different types of complex oxide material system, especially yttrium-bearing copper oxide. First high TC was discovered, which is a very interesting both structural point of view and chemistry, solid state chemistry, and also the theory, and then all this characterization, and all these things is a very rich field. And that's why I think we are here now, and I'll tell you something more about it. So I think you can see that here's a periodic table, and then it's a materials point of view. Single element has a lot of interesting properties, but the material I'm going to talk about here is complex oxide systems. The complex means it's not like a silicon dioxide. With silicon dioxide, it's just a binary, a single cation and single oxygen. So they're a very simple system. But the materials, the class of materials I'm going to talk about is a perovskite. And the perovskite is a name actually came from Russian and first discovered. And then, but sometimes people say perovskite is the garbage can of the periodic table. Basically, you mix any two cations and then oxygen, then easily can form perovskite. But it's a lot of different types of combination of perovskite, but the structure and chemistry and then physics is a very rich field. And then so you have a perovskite, most of them is clearly you need oxygen is one of the anion, we need that. And then cations, we have some cations here in the binary, and then this barium strontium in this alkaline mode. And also we have some sort of lanthanide with cation. And then B-site cations is mostly like the transition metals, and then either is this 3D, 4D, 5D, and then elements. And then this material, and then combining three elements, has a very interesting characteristics in physics point of view. It's what we call strong correlated system. It's electron-electron correlation is very strong, and also when you go higher, a 5D system, you have a spin-orbit coupling is another very important factor. So it's a play of strong correlation and the spin coupling as a rich field and creating a lot of interesting field. In terms of a structural point of view, this is the most common simple structure we call perovskite. And perovskite, as I say, A site is element is here or element here. And D site cations is mostly this D, 5D, 3D, 4D element. And then it forms this oxygen to this B site element and form the octahedra. And then this octahedra and shows very interesting electrical properties. And then that is another interesting perspective how we have to understand the nature of this. And our structure has a distortion and then energy splitting, and that's creating a lot of interesting physics phenomena. And those A site cations has a different behaviors, and then we talk about the structure and then the physical properties of this, and then we talk about how we. Okay. Can you hear me? No. No. I think the microphone with battery is not. Can you hear me? No. No. Maybe battery is coming up here. And then when you have this crystal structure, and you look at this two-dimensional plane, and either you have TiO2, the surface, or strontium oxide and the surface. You have two different types of surface can be created. So this is another thing I'm going to talk about later, and this one forms the termination of this material system, and then you make a two-dimensional electron gas or two-dimensional hole gas, and then that's what one of the topics I'm going to cover later stage of this. So interesting part of this perovskite, which is different from most of the other metals and semiconductors, and it's a large degree of freedom we can play this playground. Number one is clearly I think the charge is important factor, and then lattice important factor, spin and orbital, and all those things plays a role in this complex system. And then this one has a Coulomb interaction, and then the bandwidth plays a role, and crystal field plays a role. So I think that's a very important aspect of this material system. And in terms of this materials application point of view, and the different properties from this kind of basic building blocks, and then this the perovskite structures, and then you have very wide range of electrical, optical, and magnetic properties. And as you can see here, and then ferroelectrics, like ferromagnetic and piezoelectric, semiconductors, and transparent conductors, metallic conductors, dielectrics, nonlinear optic, and superconductors. It's all actually you can obtain, and then this kind of interesting properties from the complex oxide materials. And then when you have this kind of interesting properties, you can have a wide range of device applications, like a FRAM, like a ferroelectric random access memories, or magnetic RAM, the ferromagnetic materials like MRAMs or magnetic memories. And then ultrasound imaging from piezoelectric. This is a features. Okay. Can you hear me now? Okay. Yes. I think battery trouble. Thank you. I'll prepare this one. So you can actually see a wide range of properties like semiconductors and transparent conductors like electrodes for the type electrodes, and fuel cells, and for the metallic conductors, and dielectrics, especially new dielectrics people trying to make is high dielectric constant material for gate oxide, and then non-linear optic materials, and especially, and then you have superconductors, and then a lot of interesting magnetic sensors and transmission lines and magnets. From materials point of view, this is a range of materials, and then people have studied, like the barium strontium titanate is a dielectrics, and transparent conductors, and that this was one of the very famous materials discovered is yttrium barium copper oxide, and that is a superconductor, 90 Kelvin superconductor. And this is another cubic phase, a barium bismuth lead oxide system. And non-reacting materials like barium titanate, lithium niobate, and ferromagnetic materials, strontium luthenate, and then CMR material, we call the CMR, colossal magnetic resistance material, and lanthanum strontium manganate, and ferroelectric materials like a PZT, lead zirconium titanium oxide, and then giant piezoelectric materials, we call PMNPT, lead, magnesium, niobium, and niobium lead titanate, and then one of the important material, multiferrox and bismuth ferrite, and also very, very wide range of properties. And these are all the properties how you apply. So what's the unique of material is multifunctional materials. And as you can see, is a structural point of view. You can see that so silicon is only single element, and structure is a diamond cubic, and then structure is pretty much isotropic in terms of view. But when you look at this yttrium barium copper oxide, this high-T2 superconductors we have first discovered in 1996, and then you can see that structure is a lot more complicated. You have yttrium, barium, and copper. You have 3 cations and plus oxygen. Okay? And the stoichiometry of these is very important, but this atomic site, and here copper oxygen planes is important, important for the superconductivity. But you have an A site and B site, and also your copper oxygen planes, and then also important perspective in this, because oxygen is in and out in this system, and make yttrium barium copper oxide 7 minus delta, and then make materials superconducting to insulator. As you can see, the structural point of view, not only very complexly different, and this structure is a very anisotropic. And this one is isotropic, but this is a coherent strength, like the superconducting coherent strength, which means is how much is the superconductivity actually reach. And then this region is much shorter than A and B direction. And that's why we call this anisotropy, very strong anisotropy. And oxygen, as I said, oxygen can be in and out. So oxygen stoichiometry is very important as well in this system. And also cation doping, especially a cation doping makes this metal insulator transition. For example, first superconductor discovered, lanthanum barium copper oxide system, is without any doping of the barium. It itself is an anti-ferromagnetic insulator. But when you add dopant, that becomes metallic but the superconductors. So it's a cation doping is also very important. That's why this work in the complex oxide system is not just the physics work only. Physics and solid state chemistry and material synthesis and all different type of fields. You need to actually interact and then learn from those fields. That's why I think it's a modern research environment. You have to be really collaborative. I think that's very important. And then this is a lot of interesting properties, as I said, and then you can combine those multiple different properties. You can make a hybrid device, and then you can create novel functionality which doesn't exist in nature or doesn't exist previously. So you can actually create new functionality. And then, so one of the functionalities that people didn't actually think about is the multiferrox, is a coupling between magnetism and then ferroelectricity, or polar and magnetism can be coupled each other in the same system. So that is another interesting aspect which cannot be obtained in the semiconductor or the material system. So it's materials, physics, and chemistry, all very important in this field. So when you look at the big picture of science we approach, is very much multidisciplinary the science. And then the theory is very important, and the theory and then material design is one important aspect. And then we have to understand the structure. So it's an atomic structure, electronic structure, microstructure. All this important structure actually plays a very important role to make these interesting properties and then actual synthesis of this. So key part, what we do here, synthesis of materials. Because of material, we have, in order to have the best is, to do the good scientific work in condensed matter physics or the chemistry work. You need your material, which is a good quality, but at the same time, you understand what it is. And then you have to be pure so that you measure some properties, you really measure intrinsic properties, not extrinsic properties masked by other grain boundaries and other impurities, other junk materials. So I think it's very important. This synthesis is a really key, important piece, and that is a multidisciplinary fraction. And also, we have a discovery of new properties. The measurement of these properties can be done by unique state-of-the-art characterization techniques. And then this characterization technique always, actually, people try to, the advance of the techniques. Synchrotrons, for example, they have a higher and higher brilliance of the synchrotron beams, and then or more coherent beams, or more like a nanoscale, very, very small size of beam, so you can probe the properties which never been able to do that in the past, but actually you do push the envelope of understanding material properties. So that's important. The property is important. So I'm going to talk about some of the properties, most advanced interaction, advanced characterization techniques, and finally, and then at the end, the people ask, so what? Why you do this science? And then especially is understanding the fundamental science, but at the same time, you want to have certain types of devices, and then looking at what the societal impact. Because you do some science, why do this science? And then eventually, this science actually make a very important impact in human life. I think that's what we have to really connect all these things. So in order to do this, and then you're not just looking at just one piece of your research. I think you have to really think about, and then this. So I want to emphasize is all the research you do is not coming from like your advisor. I think it's very important. A very high level collaboration between students and postdocs. Actually, that's the work done, and then actually your advisor is a guide, and then your research directions, and then you discuss. But I think very importantly, I think you are the one actually your driver handles, and you actually key person to make that happen. I think that's why I think you have to understand all these aspects. So I'm going to talk about here is complex oxide. It's very interesting, rich field. But as I said, material is a key component to do this science. And then there's 3 different forms of materials actually people have studied. And the first form is a polycrystalline form of ceramic form. And then it's very similar to like coffee mugs with polycrystalline or random texture. And then there's grains, each grain, single crystals, is combined with the randomly oriented or sometimes textured multi-grain structure. And this is the first form high temperature superconductor was discovered. The reason is very easy to make. You just make a chemical compound. Okay, you mix the periodic table A, B, and C. Okay, you have 2 different cations. Mix it, grind the powder, put it in the furnace, and take it out, and you got superconductors. That's what the first time the surprise of superconductors is 90 Kelvin superconductor was first discovered, which is transient temperature 90 Kelvin. For the first time, they didn't know exactly what phase is superconductor. Okay, so it's a very interesting first time. So we have a lot of papers published at the time. A lot of papers is good papers. A lot of papers are wrong papers too. And because at the time we didn't know that, and then but I think it's a lot of people trying to report their findings. But later, I think we actually remember not all the papers published. We remember small number of papers, remember and cite those papers. And then your paper, be paper people remember for many, many years. And then that's an important work. I think then to do that, you have to be very understand all these things, very careful, and then we have to reapproach that way. And then this is problem of this one. Intrinsic properties of this material easily get masked by the grain boundaries or defects or all these things. So easy to discover something, but it's not very ideal forms of material that physicists like. So that's why Giabrata is working on a lot of beautiful work, which is using high quality single crystals. And the single crystal synthesis is the next step in people. And the single crystals, you make single crystal like intrinsic properties can be measured. And then, so one of the examples of single crystal is kind of, you know what this one is? Anybody know this? This one actually came from here, India. It's the largest blue diamond in the world. And then this blue diamond is initially is a big size, bigger than this, and sold to a French king. And then later, is during the French Revolution, is stolen, and then later showed up in auctions in London, different size and different shape. And there's a shape of this we call Hope diamond. And then it's why this diamond is blue with a boron is doped, and that's why diamond like blue. And when you dope nitrogen, diamond look yellow. And then this diamond, you can see this largest diamond displayed in Smithsonian Museum in Washington, D.C. So if you have a chance to come to United States and then going to D.C., and then and you can go and visit this large 53 karat diamond and very beautiful blue, and with the diamond covered and then side. And this is single crystal. And then it's all the atoms, it's a three-dimensional array, is perfectly aligned. And that is actually intrinsic properties, anisotropy or without any defect, and then you can measure those important properties. And then the problem here is anybody can find blue diamond bigger than this. Very hard to make diamond big. And same thing for these complex oxide materials, hard to grow large size of crystals. And then the reason why the large crystal and uniform properties are very hard, there's many reasons for that. When you grow the single crystal, there are many different ways of growing single crystal techniques. Sometimes people make Czochralski, sometimes make a Bridgman method, sometimes gas transfer method, but a lot of flux grown method, and many different methods people use. And then, but when you grow large crystals, and sometimes your oxygen diffusion through the large distance is very, very slow. You know, the solidity diffusion is very, very slow. The surface region is oxygen stoichiometry is good, but inside oxygen is deficient. So that's one of the problems of making large single crystal materials. And also, when you grow single crystal, it's preferable to have a congruent melting, because when you cool down, you want to have your material cool down the same composition as the melt. But many systems doesn't look like this, and that's why single crystal growth is very challenging. But a lot of creative single crystal growers make large crystals, and then they high quality crystals to start with. The material study I'm going to talk about in this lecture, most of the lectures I'm going to cover is thin films. And so this is a very exciting material form. In many reasons we study this thin films. And then thin films, you can make the dimensions is very, very small, and even thickness dimension is 1 monolayers. Okay, atomic 1 monolayers is not necessarily 1 monolayers. If you want to single UG cell formation is basically buying 2 layers, as I shown that strontium titanium crystal structure, strontium oxide and TiTiO2. You need 2 layers form the 1 unit cell. And then your lateral dimensions, and also it's easily controllable, sub-micron dimensions, and using nanometer scale, and then lithography or even lithography and X-ray lithography or focused ion beam, you can make the dimensions very, very small. And so you can actually study dimensional crossover, 1D, 2D, or 0D and 3D. We have nanoparticles and then thin films or nanowires and quantum dot type of small size dots. You can create those things very easily using thin film form. And then most of the devices we use, similar to a semiconductor device, like gate dielectrics and the source and drains and silicon and then metals on top. You stack multiple layers to actually electrode, active layers, and then you have a multi-layer structures needed. And then you're stacking of this with atomic precision, and then thin film is the only way you can do it. And bulk single crystal, you can machine it, you cannot really go down less than 20 or 30 micron dimension, and you cannot go nanometer scale, very hard to do that. More importantly, you have these two are very easily can be done in thin films, and then actually orientation can be controlled in single crystal too, because you grow the single crystal, you put in an X-ray diffractometer, and then you find the orientation, you cut it and polish it, you find the orientation. And that's what exactly like the diamond is too. And diamond is like what we call brilliant cuttings. You have 57 facets. You find the orientation of which orientation of the crystal orientation, and then that makes the diamond crystal a lot more. I mean, it's actually light can come through, and then that's the one we can orientation control. But thin films, we can start with a substrate and different orientation, then you can control the orientation. And finally, thin film can do artificial structures. And then two reasons why we can make artificial structures. First one, when you go single crystals, you grow this heated up melting point. And from the melting point, the growth of single crystal is equilibrium process, which means you cool down very, very slow, which means you have enough time to atoms move around and reach the equilibrium. And that means your phase is, we call equilibrium phase, which is, you can actually see the phase diagram. Okay, all the phase diagram is equilibrium phase diagram, and then that's what is known. But in thin films, you grow not temperature like a melting point, a lot lower than melting point. For example, strontium titanate melts over 1,000 degrees C, or we can grow single crystal strontium titanate thin films as low as 500 degrees Celsius. Okay? The 500 degrees Celsius is far from melting point, which means when you grow these materials, you do not have enough kinetic energy to form actually sometimes equilibrium phase, which means non-equilibrium phase can be formed, which we call metastable phase. The metastable is not equilibrium or stable phase, but from when you grow the material on the non-equilibrium state, going to equilibrium state, you have an intermediate state, but you have a kinetic barrier, and then you cannot go to equilibrium state because you do not have enough energy to go there. So you can actually create this synthesis of thin film coming from very far from equilibrium, so you can create metastable phase, which means it's a new phases, new materials, tremendous possibility of making new materials, which is never been existed in nature. So basically you can create new materials. First time you can make a new materials using thin films, metastable phases. Another important aspect is you can actually layer atom by atom, and then you can artificially make a superlattices, which means a super lattice means not the original strontium titanate lattice. You can actually stack different combination of A, B, or C, different elemental and different material building block, and you make up superstructures, which is new materials doesn't exist in nature. And that also create a lot of interesting physics and physical phenomena, and then that is the advantage of thin films. And I'm going to talk about a few examples of those, and then so that's a basic background of 3 different material forms. And then I'm going to focus on the thin films, but thin films not all the same, and thin films has quite wide range of quality of thin film. Some people say, "Oh, my thin film is good." What definition of good? What definition of bad? And then all thin films are good in terms of special purpose of a study or material study. But my focus here I'm going to talk about is a lot of physics students here, and I'm going to talk about is epitaxial thin films, which means is epitaxial thin film is very similar to single crystal, like a Hope diamond. And then another extreme of the thin films is a polycrystalline thin film, very similar to coffee mug, which is ceramic foam of thin films. And then you have 2 extremes of the 2 types of thin films. But most of thin films people grow is in between. Not perfect single crystal, not perfectly randomly oriented polycrystalline. It's somewhat is textured, or somewhat is grains are oriented, but not perfect single crystal. But in terms of science point of view, it's not very interesting, because you cannot really actually too complex, too complicated. In order to actually probe some kind of properties, you need very pure and a certain region of properties, especially in anisotropy. You measure anisotropy of different direction of properties different. Then you need to have is ideally epitaxial thin films. Or sometimes I prefer complete random. And then complete random, you average all the properties. So I don't care anisotropy, but as long as this grain boundary is clean, but the grain boundary is sometimes very dirty. And that's why initial high TC superconductors were discovered. And then its bulk single crystal was discovered in this ceramic form. But when you first time, when I was a grad student, and then tried to make these thin films is superconducting thin films, and then it didn't show superconductivity. The problem is it's yttrium boron copper oxide superconductors has extremely small coherent, superconducting coherent strengths, which means wave functions overlaps, and then you actually superconductivity can reach. But that is only 1 or 2 angstrom. It's a very, very small coherent strength in the C direction. And then C direction is very, very short, which means you have any disorder or a junk layer at the grain boundaries, and then like in the superconductors, you cannot have a supercurrent can go through, and that's why it doesn't show the superconductivity. And then later, people figured out that this epitaxial thin film has to be done. Then after they grow epitaxial thin film, they show the superconductivity thin film. Okay, so how they do that? It's an interesting historical background. But they found that lattice matching and substrate and strontium titanate, and when they grow thin films, and they show superconductivity, but all the polycrystallines are not good. Okay, so that's something is you have focus on epitaxial thin films, and then I'm going to talk about most of them. So thin film has another interesting aspect. Not just, as I said, they can make artificial structures, you can make metastable phases, but you have another many knobs you can control the properties. You can knob these knobs. Is one of the knobs is strength. Okay, so when you grow the thin films, you have to grow this one on top of the substrate because the thickness is so thin, like a nanometer thick. You cannot make a nanometer thin films like a freestanding like this. You cannot do that. So you have to lay down on top of the single crystal substrate. And then there are 2 types of actually growing thin films. One, you grow homoepitaxy, which means the same material grow on same material substrate. That's why homoepitaxy. when you grow strontium titanate on strontium titanate, you go homoepitaxy. And then that means you grow strontium titanate on strontium titanate, these two materials are same. And then even though you grow same material, we believe the same material, but not the same. Okay? I'll talk about that later. And a lot of different point defects. And then never is growing this exactly same material on top of this, extremely challenging. And people didn't realize those things until recently, and they developed a new process to make this strontium titanate itself almost same as the single crystal bulk material. And then stoichiometric control is extremely challenging because of like a less than 0.1% of the stoichiometry, it can change this properties very dramatically. Okay, so I'm going to talk about that. One of them is important aspect of point defects later too. But as I said, this homoepitaxy is one example. But more exciting part is coming from heteroepitaxy, which means grow different materials on different substrate. Okay? So that means we grow strontium titanate material on top of barium titanate, or your barium titanate on strontium titanate, and then we grow those. We call this heteroepitaxy. So the hetero means a different, homo is the same. So the homoepitaxy or heteroepitaxy. Epitaxy means is a registered growth. So you grow the materials. I see what is the pattern of underlying pattern, and then you actually lay down atoms. You follow the patterns of the atomic arrangement. That's why we have epitaxial growth. So one of the important knob I'm going to talk about here is strain. And then this is one example of the previous actually work. I'm going to talk about that later. And then barium titanate is known as a ferroelectric. And then below 160 degrees Celsius. And then below that, and this one goes to paraelectric to ferroelectric phase transition around 160 degrees Celsius. And high temperature, and then this paraelectric phase is the same as strontium titanate, the cubic phase, which means A, B, and C is all the same lattice parameter. And then this titanium B site ion is centered with respect to the oxygen. So that's the same line of oxygen. So there's no net actually polarization or net charge, actually remnant polarization in this system. So when you go through the phase transition, and it goes the phase transition from cubic to tetragonal phase, which means the C lattice parameter longer than A and B lattice parameter, because structural phase transition goes to cubic to tetragonal phase. But at the same time, it goes to paraelectric to ferroelectric transition, means you have remnant polarization. Is spontaneously your atomic position, so titanium is not exact center of it, it's off center with respect to oxygen ions. And you can have either up and down state. You have two different stable regions of free energy diagram. So you have two different locations, and either up, you have a down state, and you have a those state. And those things can be controlled and switched by external electric field. So when you apply electric field, you switch up and switch down, so that creating 1 and 0 state, a logic device. That's why people make this material for ferroelectric memories. Okay? So why does this strain engineering can do? As I said, in the barium titanate system and ferroelectric, you have a elongation of 3 direction, the tetragonal distortion, make this material stronger ferroelectric, larger remnant polarization. And then how you can make this more stable and then actually larger polarization, and then very much higher temperature you can maintain the ferroelectricity. So in order to do that, it's very simple. You make this one more tetragonal. You distort it more. Then intuitively you can think of, without thinking very complex, without help of the theorist or calculation or computation, just simple intuition. Okay, I mean, just this one you can think of, even undergraduate students can think of this phase diagram. Okay, you press more, maybe more stable. How you can press this one more? Okay, you can take a boxing crystal. I will take this boxing crystal. I want to press it. Okay, how much you can press this by single crystal ceramic material? I can take a. Can you press glass door? You take a glass door. How much you can press it? You press too much, you break it, because it's all this ceramic material is very, very brittle. So you cannot go more than maybe less than 0.1%, easily can break it. But in thin films, is you can actually apply the strain few percent without breaking it, which means tremendous amount of strain without breaking this, and then those kind of strain regime, you cannot do that by bulk materials. You can do only thin films. Or you can make a nanowires, you can do that. But thin films, you can compress this easily, large amount of strain. And then, for example, this is the phase diagram, prediction by phase series, some other calculation. When you press and compress this, like a 1 or 2% of strain, your ferroelectric transient temperature increased dramatically. Okay, few hundred degrees Celsius, you can increase it. And then, for example, all right, so can you apply roughly 1%, or can you apply 1.7% or 5%? How can you apply this? And you have to find the substrate material. Lattice is different. Lattice parameter is smaller than this. Which is smaller than this, you grow this material, this lattice parameter of dimension this, you compress this. But I compress this uniaxial, but not uniaxial, biaxial. So all direction, press it. Then because the volume is conserved for Poisson's ratio, only way you can do it, elongated that direction. Okay, so that's what happened in the barium titanate, the elongation of that direction. But in the biaxial strain, is to compress it, make it smaller. So those things actually can be done here. In boxing crystal, you have phase transient temperature is 160 degrees Celsius, but when you compress this using substrate, we call gadolinium scandate and dysprosium scandate, those two single crystal substrate, so you can see the different color of this, and then you can grow and this material on top. You make transient temperature is very high, like 500 degrees Celsius. And then this is a similar type of turns, cubic phase to this split of the A and B lattice parameter, and then you can see that C and AB lattice parameter, and you can see the split, and then it's a half dome, and basically it's forming like this, C and A. So in plane lattice parameter here, and out plane lattice parameter here, so you can actually see that huge change of lattice parameter. Now that is one of the examples of your strain thin films, epitaxial thin films. You have very important knobs. You can control the properties and dramatically enhance the material properties, or you can actually find the new functionality and new properties never seen before, because you compress your strain, you can apply a few percent, which cannot be done in boxing crystal. So that's one of the knobs, but you have more than one knob controlling thin films, and that's why I think it's complex oxide materials. You have rich electronic, optical, magnetic, and then these multifarious properties, but that's not all. You can actually engineer and design the materials in thin film form and then control the knob. You have a tremendous actually playground. You can actually use this lot of interesting materials, and you can control this. You can discover new physical phenomena. You can discover new materials. You can actually study new physics. You may create new devices maybe down the road. You have those new devices can be applied to another functionality, like not 10 years down the road, maybe it's like a smartphone is no longer exist. Maybe your different functions and different device can be used. Maybe those functions needed at the time using this. So that is some background of this. But at the same time, and then another one, this is another example. This is maybe one of my last lecture, is nickel superconductor. This is another unconventional superconductors. And then your thin films is critical condensate is enhanced tremendously. And this is the Satyavrata's early work of the superconductivity work is flux fittings and the superconductivity, and in the NGV2, and then is a magnesium diboride thin films. But I think this is the one is nictite, is the superconductors, and you have this bulk single crystal. Is the flux pinning is very weak. The bulk single crystal is only 10 to the 6th or 10 to the 5th low, but epitaxial thin films is a 1 or 2 order of magnitude higher critical density you can obtain. And this is because we have a more flux pinning, like the defects can pin the flux so that you can have a large current can apply without losing the superconductivity. So that's the one of the examples, and then we talk about it later. So now I think I have enough background, some interesting excitement of these complex oxide materials. And I'm going to give a little bit of interesting background here. And then we need atomic layer control. I'm going to spend some amount of time here, atomic layer control goals, and then a couple of lectures. And then when I started initial growth of these high TC superconductors in mid-1980s or early 90s. And then at that time, one of the major challenge of the actual thin film growth is not that one. The major challenge at the time is just stoichiometric control. Even at that time, we don't know how to make yttrium 1, yttrium 2, barium 2, copper 3, 1, 2, 3. Stoichiometric control is challenged at the time. Very difficult to make 1 to 3 chemistry. Now everybody knows how to make 1 to 3 chemistry easily, but at that time that's a challenge. And later, people trying to make a thin films, and thin films, okay, how we can make an epitaxial thin film is another challenge. But it's actually challenging more and more difficult, and more challenges come, which is really can you control atomic layer control as good as semiconductors? Because this is the quantum structures, like aluminum arsenide, like aluminum arsenide structures, and that's actually studied for many years, MBE and molecular wave epitaxy, and they developed this kind of the level of wave epitaxy. And then, can you do this level of epitaxy? And that's another important, actually, many years development of this thin film growth technique. Okay, so how can you do that? And then, as I said, initially, just growing stoichiometric thin film is a major challenge. But from there until now, we can achieve this level. But your student, your career or your scientific career is many years down the road. Maybe you're doing this science in 40 years, 50 years or something. And what is the next challenge of the synthesis of these materials or discovery of new things? And then you can actually imagine something is to push the envelope of not only synthesis and other types of characterization and discoveries. So this kind of growth is multiple step of advancement is needed. Okay? The first important step is growth thin films. So when you grow your thin films, you can actually think about very similar to building houses. Okay. First, you have to find your foundation. Your foundation of thin films is substrate. You need a substrate. Start with a certain substrate. But many years we have never thought about this kind of concept of termination. We just get the substrate from the vendor, Okay, how they make a substrate. You just get the single crystal, very similar to polishing of the Hope diamond, or I have seen in a lot of beautiful gemstones in India. When you get the crystals and cut it and polish it, that's exactly the same process. We get single crystal and substrate. They polish it, and then it's like the atomically flat. They want to make those things, but when they polish those things, and then that has a mixed termination. As I said, in strontium titanate, looking at very atomic scale, we have two different terminations. One termination is like this. You cut it, this region, you look at two-dimensional surface, looks like this. Okay? There's a strontium oxide termination, strontium 1, oxygen 1 is termination. You look at this surface, titanium O2 termination, it's a 2 oxygen, 1 titanium, TiO2 termination. When you polish those things, and then surface looks like this, a mixed termination. Certain region, the TiO2 looks like this, certain region looks like this. When you heat it up at high temperature, then your atoms move around and forming large patch of different regions. This region is a titanium termination, TiO2, and this region, strontium termination. This is done by, we call, friction contrast. When you do AFM scan, your lateral scan can actually see that the friction, there's a friction between AFM tip and surface of atoms, and depending on your termination layer, and you have a different friction, and you can see the very strong contrast to different terminations. Then we grow the thin film on top, and this region and that region, film grows differently. And for example, simply we grow one material and lay down here very flat, beautifully well. And this region looks like doesn't wet, like you have a water droplets, like a droplet like this, doesn't wet, like a very much island grows. So a very strong contrast, two different regions, very, very different. So how can you make your films uniformly everywhere, same kind of quality? How can you do that? So that's one of the challenges we have to do is make the materials, your substrate material, either well-defined single termination. So that's what you do. Can you make just 100% this termination and everywhere your substrate? And then this technique is developed by the couple of groups. One is a Japanese group, another one a Dutch group. And they made this one is terminating 100% of TiO termination. The basic background of this is a very simple chemistry, because strontium is more basic than TiO2. Okay? So your base layer, a little bit of basic layer. So which means it very well easily can dissolve in acid. But you don't want to put very strong acid. If you put in strong acid, it will dissolve everything. But you have a some kind of borderline. If very, very weak acid can only preferentially attack strontium oxide layer, not TiO2 layer. So that is a buffered HA, like a buffered hydrofluoric acid, very dilated, buffered one. And then that only attacks strontium oxide layer. And then you can create a beautiful single surface termination. And then you can actually see, you look at this atomic force microimage. Anybody done for AFM imaging here? You need the AFM imaging. And then this is the step height, your section analysis. This is actually step heterostructure, typical step heterostructure you can make in thin films. You can actually see here, step 1 and go up, up, up here. Each step is 4 angstrom, which is same height as this height. Okay? There's full length height, because the titanium layer and next to titanium oxide layer, there's roughly 4 angstrom. exactly 3.905 angstrom, but roughly 4 angstrom. And then each step is 4 angstrom, okay, roughly. And you do not see this kind of half initial steps. When you scan this region, I don't have an image here. When you scan this from here to here, strontium oxide to titanium oxide, these steps. So that is roughly 2 angstroms. So you can actually either 2 angstrom step, you can see the 4 angstrom step, and that is a mixed determination. But another important fact is your very well defined long terraces. So at least these regions when you grow, you have everywhere no steps and single surface termination. And that's the first important aspect. You make your material single surface termination. The next one you do is not only using substrate, you have to grow thin films really atomic layer control. Then how do you know this atomic layer control? And then we adapted this technique from MBE, because your molecular band taxi, the semiconductor growth, they use, so they call this in situ monitoring technique, use reflection, high energy reduction diffraction technique, which is in situ real time is monitoring of the growth. Both like how fast you grow, what the structure is, and those things we call real time monitoring of the growth. But those monitoring growths, we cannot use those things. It's available for MBE. The growth condition of MBE is ultra high vacuum, which means the vacuum level, you don't want any gas, like an atmosphere, the purely high vacuum. Your only flux is coming from your elements you're depositing. That's a 10 to minus 9 or 10 to minus 10. Your base pressure is that good. Then your atoms just to have 100% of atomic flux and molecular beam epitaxy. But in thin films, your source of oxygen is gas. Because think about it, you have a strontium titanium oxide, you have this kind of strontium titanate. You have 2 cations, strontium and titanium cations, coming from metals, or you can have a solid source. You can provide those things. For oxygen, it's not solid source. Oxygen is gas source. You have to provide the oxygen from background gas, which means you have plenty of gas oxygen needed to stabilize this phase. How much oxygen you need? How much you need this kind of oxygen to stabilize certain type of material that depending on what material you grow. Some material needs tons of oxygen, some material needs very little oxygen, and depending on your stability of your materials. For example, in the yttrium barium copper oxide, and this phase diagram actually people studied, is this oxygen partial pressure and this temperature, and depending on temperature, your oxygen partial pressure, this is the regions of you can stabilize yttrium barium copper oxide superindenting phase. Below this region, your oxygen partial pressure lower than this will decompose to this different compound. So that's you don't want. So you need minimum oxygen partial pressure above this region, which is relatively very high. And then other one, like this other material system, your different oxygen state, you have multiple phases depending on oxygen content. Your V2O5 to like pure vanadium, and different temperature and different oxygen partial pressure. You have different regime. You have different types of vanadium oxide. Okay, so that means you really need to control oxygen partial pressure during the growth. But sometimes you need most of cases, large oxygen, high oxygen partial pressure stabilizing. But these two are conflicting problems. One is your MBE type of growth,
you need the ultra-high vacuum and to control the in situ monitoring of atomic control. But at the same time, I need to provide a lot of oxygen to stabilize this phase. How can you overcome this problem? So the way I know explain this read, I can talk about this read pattern. And this in situ monitoring is two different information you can get. The one information is how smooth of your film. That's the one information. And another information is what is the actual lattice structure on the surface. There are two information. One is morphological information. Another information is atomic structure information, crystal structure information. And those information is shown here. And then I'm going to show you here what is this concept. So this V, his full name is reflection, high energy electron diffraction. Okay, reflection, high electron energy diffraction. So what that means? So just simply, I have this iPhone here, and that is a very shiny mirror surface. And then when I blow in the surface here with, okay, can you see this one is a very bright reflection here? Can you see this one? I reflect here, and this is very bright. Can you see that? Okay, I'm going to blow here my steam, and then whether this light is going to be as bright or dim. I'm not sure. I never tried it. I'll try it, see what happens. And then not as good because it's not a good test. But you can actually do, just simply, you can think about this. When you wake in the morning, I think it's some people, they shave in the morning, when you turn hot water. And then when you turn hot water, your mirror is condense a lot of water droplets. Then you really cannot see your face because all condensation water. But after dry out, you can actually see that, you can see it well. But this is just one layer of this. But you can use the same kind of laser pointer to go home when you turn hot water and you reflect it. And then initially very bright. When your condensation happens, then this one is a dim. Then once it's gone, then bright again. It's a very similar concept of this, but this wavelength of this laser is a few hundred nanometers. The size of water droplet is scale of microns or much bigger. And then, so that means it's scattered, this few hundred nanometer beam is size of droplet of the morphology, and then scatter this, very similar to this. But when you deposit atoms, size of atoms or islands, how small those things may be order of 1 nanometer or like an angstrom scale. And then a few hundred nanometer wavelengths feels like is nothing. Can you imagine this? Wavelength is too long. Wavelength is so long compared to size of this, and then it doesn't feel anything. So that's why if you just the same kind of laser, and on the surface a lot of atoms attached, no difference. But how can you make your wave small enough, very close to size of atom? Which one you can do it? X-ray, you can do the X-ray, but X-ray is one way to do it, but actually that's quite deep. And then use the electron beam. The electron, high energy electrons, like roughly 20 or 30 or 40 K electron volts. And you can calculate what the wavelength of the electron beam. That's a sub-angstrom wavelength. And that's why you can make atomic imaging of transmission electron microscope. And then that wavelength is really can see that atoms on the surface, what the difference is atoms. So what that means is your electron beam scattered same way. Surface is no atoms attached on the surface, flat, like this. Like this. Surface flat, no atoms attached. Then you will see its intensity of reflection is very, very bright. Okay? And this bright beam here initially, and when your atoms arrive on the surface atoms, then same way, like a water droplet on the mirror and reflection of this scattered everywhere, and the intensity go down. And this intensity goes down when you have roughly 50% coverage. And 50% coverage, you go down at minimum. Then when you go another full coverage of this, then you go back again. So that's a one single oscillation corresponds to one monolayer. So what that means is you really can see one atomic layer by one atomic layer control, just monitoring, counting this oscillation. So that's one way. And then this is commercially available now, but at the same time, you can actually see your diffraction pattern, your electron diffraction pattern, like very similar to TEM, and then what you do in actually the lattice crystal structure imaging, and you can actually see either polycrystalline, amorphous, and then 3D island. You can actually see all these structures, and those things can be done using we call high pressure read. You operate this one very high oxygen partial pressure. You can see that your oxygen partial pressure in high oxygen partial pressure to operate it. And you do that, you can actually see this read gun has two problems. One problem is how you can generate the electron beams. Anybody know how to generate electron beams? The electron beam is simple thermionic emission. You heat it up, high temperature filament, and electrons overcome the vacuum level, and electron come out, and you accelerate from the electric field. And using some coils outside, and you bend the electrons and focus the electrons. That's what basically you do electron gun. And then you have a tungsten filament. Temperature very high. You have oxygen. Then what happens? You burn filament. So you don't want to have any oxygen in this filament side. But in the vacuum chamber side, I need a lot of oxygen. Then how you actually do those two things? And another problem here, you have a lot of oxygen here. Then oxygen gas molecules actually scatter the electron beams. So that means if the mean free path of electron beam can be very short. So your mean free path is very short. That means the normal read guns, read work in semiconductors very far distance. Like from electron beam to sample to actual imaging plate is this very long distance, and then you can do the image here. But if you have this long distance, it all scattered, you don't see anything. So in order to do that, you have to make this distance very close, very short. Not like a meter distance. It has to be 5 centimeter distance or 10 centimeter distance. It's like a factor of 10 smaller distance to make this image possible. So in order to do that, basically two things. One is the electron beam, its axis of electron beam is very, very close to this sample. And this phosphorus screen imaging of the read pattern is pushed into the chamber. Its distance from here to here and distance here to here, only a few centimeters, very, very close. But your exit of electron beam, the hole diameter is few hundred micron. Very, very tiny holes, and then your differential pumped. Basically, you have a pumping of this chamber, so your additional pumps, okay, evacuate this additional pump, maintain, there's two different pumps, maintain inside this region vacuum, 10 to minus 6 or lower, but in this region, you can actually maintain close to 1 torr of pressure. So that means 1 torr, 10 to minus 6 torr, your differential pumping ratio is roughly 10 to the 6th. You need large differential pumping ratio because you have very small tiny holes, and additional two-stage pumping make this region is a good vacuum. So that means you have from traveling electron beam from here to exit of the beam inside the good vacuum. So the mean free path is very long, and then you can actually travel without scattering. You can exit here, then this one's very close, and you can see that. So that's one of a very important step to make this atomic layer control in situ monitoring possible. And then you can see this diffraction pattern is done very high pressure. You can see the beautiful pattern. And this is done 50 millitorr of oxygen partial pressure, growth of strontium titanate. You can see that very nice oscillation. Okay, this is real data. Okay, when you grow this, you see the oscillation, which means okay, this is 1 4 angstrom, another 4 angstrom, so one layer, another layer, and that is possible by this method of the read. And doing so, you actually grow this typical strontium luthenate. It's a material. It's another perovskite. It's a very interesting perovskite, and it's basically this is the iterant ferromagnet and also spin polarized ferromagnet. And then this material was drawn on this substrate. And then I just want to show you real-time imaging of this and strontium luthenate and strontium titanate and strontium luthenate, a tri-layer structure. When you grow tri-layer structure, and you can make first layer. Okay, this is the bottom layer. Let me see the bottom layer here. There's bottom layer. You see that this kind of pattern. I'm going to talk about these details atomic layer control in another lecture. And this is we call step flow growth regime. And strontium titanate grows like island growth, two-dimensional island growth. Strontium luthenate go back to step flow growth. I'll talk about that later, why this thing happened. And then, so anyway, you maintain very nice step structures. And then when you look at cross-sectional micrograph, and this all layers perfect single crystal. And you can see, and then there's no grain boundaries and no dislocation, which means fully coherent. And then lattice parameter of strontium luthenate is larger than strontium titanate, so it grows like compressed, biaxially compressed, and grow like this. And then strontium titanate, very thin layer strontium titanate sandwich between here, and you can see that completely single crystal. And another example is a ferroelectric tunnel junctions. Strontium luthenate, barium titanate, and strontium titanate, and strontium luthenate. And there's a metallic layer so that you can apply electric field. You can switch it. But you can see that barium titanate layer extremely flat. And then you can count how many barium titanate layer, and those things is counting how many oscillations. After grow all the layers, and surface is atomically flat. So this is the level of the epitaxial thin film growth. And let's go back and compare this structure, and compare the structure I show you already. This structure. Okay, so that is how semiconductors and then approach to make a quantum wave structures and making fractional quantum wave effect. Now we have a complex oxide materials, much more complex chemistry, much more complex materials. Now we have a level of epitaxy is their level. So I think at this point I think we have discussed clearly what is materials exciting, what is exciting materials, and then different form of materials, ceramics, thin films and single crystal, and single thin films have epitaxial thin film, quadrilateral thin films, and why epitaxial thin film is exciting, and then what knobs we can control, and then we have a lot of challenges of synthesis, but those challenges overcome by using atomic control. And now with the level of the perfection and level of control is so reach that point, and really we can study real science of intrinsic material science physics of this. And because you have a handle, you have an extremely large playground of this all the exciting material system, but you have a handle of knobs, you can actually make these materials what you like to actually create and discover and find some interesting devices. I think right now, I think we'll have roughly hour and 15 minutes, and then I'm going to invite you some questions, or I can go a little more other slides, whatever you like. And then I have many slides to go, but I think this is just something brief introduction, because I want to make this first lecture excitement. You want to be excited to come to this lecture. This is boring lecture. Why I come here? This, and this is your field of something I want to study. Oh, I want to join this field, and then this tremendous opportunity to actually study, and then you make a big impact in both societies and science advancement. Okay? Any questions? When you ask questions, can you raise a hand and give your name? Then I think over time of 2 weeks, and then I can remember everybody's name, so that in the future you have communication, I remember who you are.
One general question.
Yes.
Like barium titanate, we have strontium titanate. They are isostructural.
Yes.
In bulk, I mean, I'm not following this field much, but I remember that bulk strontium titanate doesn't show spontaneous ferroelectricity. It's believed to be a quantum paraelectric. And you showed this interesting slide that the strain can act as a field which induces polarization. Does it also happen in strontium titanate?
Yeah, that's a really excellent question. Actually, strontium titanate can be ferroelectric by 2 different ways. And one paper published about the same time we had barium titanate paper, and one paper by Darrell Schlom's group at Penn State at the time, and then in the Nature. I'll bring those phase diagram when I will show ferroelectrics and then strain engineering when I show. They have a calculation of strontium titanate phase diagram, not symmetric, it's asymmetric. So asymmetric phase diagram. So you get its compressive side, you have a slope is low, and tensile side is slope is much steeper. And then so they use the strontium, not actually compressive one, the tensile one. Strontium titanate lattice parameter actually smaller. So they wanted to have a larger lattice parameter, actually stretch it. Rather than compressing this, you actually, this one stretch this way, stretch that way. And that actually make strontium titanate room temperature ferroelectric. And then using dysprosium scandate or gadolinium scandate is enough lattice mismatch and strain room temperature ferroelectric.
That's already interesting that it's behaving differently to compression and stretching.
That's right.
But the other part of the question is it infinitesimally sensitive to stretching or compressing, or does it take a critical stretching before it starts showing a ferroelectricity?
That's a very similar phase diagram I show.
Okay.
The slope, you can see the slope.
So all the way from 0 you are saying?
That's right. Yeah, from 0% is non-ferroelectric.
Yes.
It's a very, very low temperature. It's a non-ferroelectric.
It's a quantum paraelectric.
Exactly. Yeah, exactly. So when you go temperature, is a raised like this,
Yeah.
and you need ferroelectric around 1%, 1.2%, and that's the region room temperature ferroelectric happens. But when you have like a stretching more, then you have like a room temperature, not even higher temperature in ferroelectric. That's a one strain engineering is one way to do. And another way we actually discovered that's in 2015 is strontium titanate, this point defects. It's one of the major point defect is a titanium anti-site, which means the strontium site, if strontium is a vacancy, then size of strontium vacancy is big. And titanium goes into the site, then your room is too big. So that if titanium is not centered, it's off-centered. So that actually creating what we call polar nanoregions. It's not really spontaneous polarization large scale, but a patch like this. And then when you have this patch on, when your dimension gets smaller and smaller, this patch can be faced to the whole surface of the bottom electrode and become ferroelectric. That's published in 2015, published in Science. And that's what we call ferroelectricity at room temperature at reduced dimension. So that's something I'm going to talk about that later. And that's it's a lot of, you brought a very important question. And there are two ways we can do it. And then that's why you can actually not only enhancing the ferroelectricity of the certain material, you make non-ferroelectric to ferroelectric, you can do it. The next one lecture, I will talk about something is polar, non-polar material to polar by structural engineering, which is another one I'm going to talk about. But I think, you should come to my, I think it's a very good question. I think this kind of question, I like to have your action from this class, and there's no stupid question. I think this is all good question. And I like to invite your questions. This is your time. This is your lecture, and I'm come here and then share a lot of things. But I think that this I like to hear what you think and what you have in mind. Your question. I never given this many 2.5 hours twice, but I think maybe my voice is maybe losing a little bit later. But I think I try my best because most of my class is 15-minute class. But this is a little too. But you can take a coffee break.
Yeah,
and
you
then,
can take a break in between.
Yeah.
Almost, 5 minutes. So we meet again at 4:30.
4:30. Okay. All right. So we can the break and then come and then talk to me and then this is I like to have get to know each other and then. All right. Okay. Thank you.